discussed at length the predictions that arise from the following recursive model for the growth of an age-structured population. You'll probably remember that x1 at t gives the number of juveniles in our model population at time t, and that x2 at t gives the number of adults in our model population at time t. You'll probably also remember that the matrix 0 to 0.3, 0.8 captures the demographic assumptions that we made, and that it's these assumptions that determine the number of juveniles and adults, respectively, found in our model population at time t plus 1. In earlier videos, we took our recursive model and modified it to capture the change in the age distribution that occurred between times t and t plus 1. When we plotted this modified version of the model, we were able to see that, in the long run, the population it represents is predicted to grow. In this case, grow without bound. More recently, we used the same model to derive a nice, tidy expression for the relationship between the age distribution and time. You'll recall that relationship was built around the eigenvalues and eigenvectors of the matrix associated with our original recursive formulation of the model. With this model, we could develop clear quantitative predictions about the age distribution in future time periods. Given that we've approached our original model in these two distinct ways, it seems natural to wonder whether we can see how the predictions we made in each case coincide. To address this question, let me make a couple of points about the more detailed model we see here on the right. Let's focus on this bit here, and in particular, on this number in brackets. It's one of the eigenvalues of the matrix of our original model, and it's roughly equal to negative 0.472. With that in mind, when we raise this number to the power t and then take a limit as t becomes large, the result will tend to 0. That means that the entire part I've enclosed in the rectangle will tend to the 0 vector. Basically, given enough time, this bit doesn't factor at all into our predictions. What does factor into our predictions, even in the long term, is this part here. In fact, this number here, also an eigenvalue of the matrix associated with our original model, by the way, happens to be greater than 1. Consequently, as time goes on, it just grows and grows, and given enough time, our predictions are basically dominated by the part I've enclosed here in this second rectangle. This dominant effect exerted by the terms means that the total numbers of individuals in the population grows, but it also means that their distribution across age categories begins to closely resemble this vector here. Specifically, for every 2 juveniles in the population, we expect to find 2/5 plus the square root of 19 over 5 adults in the long run. The dominant effects of certain terms in our detailed model can be picked up in the illustration here on the left. We've already noted that the population is growing without bound. The predictions of our different approaches coincide on that point. What we also see in this diagram here is that the flow eventually tends to follow this line. And this line has slope 2/5 plus the square root of 19 over 5 divided by 2, as predicted by the dominant terms in the detailed model on the right. Overall, what we're seeing here is a consequence of a mathematical result known as Perron's theorem, or rather an extension of Perron's theorem. Perron's theorem applies to much more than models of age-structured populations. So let's put this model on the back burner and take a closer look at the underlying mathematics. Perron's theorem tells us about certain key features of positive matrices. That is to say, matrices whose entries are all strictly greater than 0. If a square matrix A is positive, then Perron's theorem says that A has an eigenvalue that's greater in absolute value than any other of its eigenvalues. We often refer to this greatest eigenvalue as rho, or the dominant eigenvalue, for reasons we'll get to. Perron's theorem also says that the eigenvalue rho is a positive real number and is associated with one and only one family of eigenvectors, represented here simply as U. Because U and multiples thereof are associated with rho, we sometimes refer to it as the dominant eigenvector. A third point of interest that comes from Perron's theorem is the fact that we can choose the entries of the dominant eigenvector U so that they are all strictly positive, and of course real. It just so happens also that U and multiples of U are the only eigenvectors of A whose entries can all be made to be non-negative. Finally, and this is an important one, Perron's theorem says that if we apply a positive matrix repeatedly to some vector, the result tends to a multiple of the dominant eigenvector as the number of applications of the matrix increases. As I said, these consequences of Perron's theorem can be seen in the previous example. Let's briefly return to that example to see what I mean. We see that the matrix from our age-structured model had two eigenvalues, and, in keeping with Perron's theorem, the absolute value of one of those eigenvalues was greater than that of the other. In addition, the eigenvalue that has the greatest absolute value is itself a real number, it's positive, and it's associated with an eigenvector whose entries can also be made to be positive. Contrast that to the situation we have with the other eigenvector associated with the other eigenvalue. You'll notice that there's nothing we can do to change the fact that one of the entries of this eigenvector must be positive and one must be negative. In other words, we can't exercise the choice we have when constructing this eigenvector to ensure that all of its entries are non-negative. You can see that the largest eigenvalue in absolute value and its eigenvector both factor into the terms that dominated the predictions of our age-structured model as time passed. It's for that reason this eigenvalue and its eigenvector are referred to as the dominant eigenvalue and dominant eigenvector, respectively. In biological terms, and in keeping with our previous discussion of model predictions, you might also reasonably refer to the dominant eigenvalue in this context as the long-term geometric rate of population increase. When the dominant eigenvalue is greater than 1, the age-structured population eventually grows without bound. And when it's less than 1, the age-structured population will eventually tend toward extinction. As we suggested before, the dominant eigenvector describes the relative numbers of individuals that eventually come to be found in the various age categories in the population. With that in mind, you might not be surprised to find out that, in models like this one, the dominant eigenvector is also called the stable age distribution of the population. It's stable in the sense that the same relative numbers of individuals are eventually found in the population, regardless of whether the population itself is growing or shrinking in size. Just like Perron's theorem predicts, after we apply the matrix associated with our age-structured model enough times to the initial age distribution, the distribution itself comes to resemble the dominant eigenvector ever more closely. Now, there's one important issue I've neglected so far, and it has to do with the matrix associated with our age-structured model. You might have already twigged to the fact that Perron's theorem tells us about positive matrices, but not every entry in the matrix associated with our age-structured model is a positive number. So why, you might ask, does Perron's theorem apply in this situation? The short answer is that it doesn't apply, but an extension of the theorem does. That extension of the theorem covers an entire class of non-negative matrices. In other words, matrices with entries that are 0 or greater. The class of non-negative matrices covered includes the matrix we were working with. In general, the non-negative matrices to which we can apply the conclusions of Perron's theorem have to be what we call primitive matrices. In order to qualify as primitive, a matrix must first be irreducible. That is to say, it must correspond to a model that doesn't keep track of superfluous information. The model we were working with, for example, is irreducible because we consider only those categories of individual that are absolutely necessary to understand population growth. Had we tracked, for example, deceased individuals alongside juveniles and adults, then our model would not have been irreducible. In this case, keeping track of deceased individuals is superfluous in a modeling sense, because doing so doesn't give us any extra information about population growth. Once we have established that a matrix is irreducible, we can diagnose it as primitive by looking at the network diagram to which it corresponds. To illustrate, I'll show you how we can see that the matrix from our age-structured model can be seen to be primitive by looking at the network we use to construct it. Looking at this network, we first ask, how long is each path that begins and ends on the juvenile's node? By path, we mean a route through the network that follows the arrows but doesn't travel along the same arrow twice. By length, we mean the number of arrows that must be traversed during our trip. We see that, starting on the juvenile's node, there's a path of length 2 that brings us back to this node, and one of length 3 that does the same. With those numbers in place, we then ask, what is their greatest common divisor? That's an easy question to answer since we have at least 2 prime numbers in our list. The answer, therefore, is 1. We next move to the adults node and ask the same questions. How long are each of the paths that begin and end on this node? It's not hard to see that the lengths in this case are 1 and 2. And the greatest common divisor of these numbers is again 1. The fact that we've come up with a greatest common divisor of 1 for the path lengths at each node in our irreducible network allows us to conclude that the matrix upon which it's based is primitive. Ultimately, this means that we're justified in applying the conclusions of Perron's theorem to this matrix, as we did earlier in the video. In general, to show that a non-negative matrix is primitive, we must first determine that it's irreducible. Then, we go node by node, counting paths and finding greatest common divisors. If the greatest common divisor of path lengths is 1 for each node, then we can say that the matrix is primitive. If the greatest common divisor is not 1 for every node, though, we would say that the matrix is not primitive, and in this case, we'd have to rethink the application of Perron's theorem. Here's a quick recap before we wrap up. In this video, we revisited the long-term predictions arising from a model we constructed to capture the growth of an age-structured population. We saw that those predictions were in line with the conclusions of something called Perron's theorem. Even though Perron's theorem tells us about positive matrices, we saw that its conclusions apply to certain non-negative matrices as well, like the one featured in our age-structured model. Broadly speaking, our ability to apply the conclusions of Perron's theorem to a non-negative matrix rests on that matrix being primitive. By the time you've mastered the ideas presented in this video, you'll be able to do 3 things. First, you'll be able to state the conclusions of Perron's theorem and verify when these apply to a given non-negative matrix. Second, you'll be able to provide a biological interpretation for the largest eigenvalue, in absolute value, and corresponding eigenvector of a matrix that is itself connected to a model for the growth of an age-structured population. Finally, you'll be able to apply Perron's theorem to derive long-term predictions arising from matrix-based models, like the one we developed for the growth of an age-structured population. As always, read, try the problems, and engage, and success won't be far behind.